Okay, let us continue with the chapter 6 solutions of Razavi textbook. So in problem number 6.41, so it is given that if lambda is equal to 0, what is the value of lambda by L to place M1 at the edge of saturation in this particular figure. So this is the figure 6.53 what we are looking at. So we are asked to find what is the W by L to keep the MOSFET in saturation condition. Now as you can see, now the gate is at 1 volt, the source is connected to 1.8. we can actually find what is VGS magnitude. So VGS is actually minus uh, 0.8 volts. So magnitude wise VGS is equal to 0.8 volts, which is greater than 0.4, which is supposed to be there for a PMOS transistor in terms of magnitude. So MOSFET is on now. So now we have the expression for magnitude of the current for a PMOS transistor as mu P Cox by 2 W by L, and magnitude of VGS minus magnitude of VTH whole square. So out of this we are asked to find what is W by L. We know what is VGS, we know what is VTH, but of course we know what is mu P Cox also. Mu P Cox is given by, as you can see now, this is 100 microampere per volt square. We don't know ID, we don't know what is W by L. So since the hint given is that the MOSFET should operate in at the verge of at the verge of saturation region, since magnitude of VGS is 0.8, the V threshold voltage magnitude is 0.4 volts, the VDS sat happens to be 400 millivolts, meaning that between drain and the source we are supposed to have 400 millivolt between this and this. So we know that the supply voltage is 1.8 volts. So when the supply voltage is 1.8 volts and the voltage that is to be maintained across drain and source is 0.4, meaning here this is 1.8 minus 0.4 is to keep the MOSFET in saturation. The remaining voltage is 1.4. So we can find the current ID over here. So where current ID is given by 1.4 divided by 2 kilo ohms. So that's what is done here. So now we can see the ID is given by VDD minus ID into RS is actually 1.4 volt. So ID is nothing but ID is equal to 1.4 divided by RS, where RS is the source resistance which is connected the sorry, this is at the drain resistance. So we know that this is 0.7 milliamperes. The drain current is now 0.7 milliamperes. So using the equation what we had earlier, so 0.7 milliamperes is equal to mu P Cox by 2 W by L, and this is VGS minus VTH whole square. So this way we can actually estimate the value of W by L. You can use the alpha. Okay, you can write 0.7 milli is equal to alpha equals mu P Cox by 2, whatever the value that is given. Make this W by L as alpha A and solve for it. Shift solve twice. We're going to give the W by L as 87.5. To move on to the problem number 6.43a part. So here W by L is given as 10 divided by 0.18. So considering lambda as 0, we are asked to determine the operating region of M1. So in this particular figure. Now, so let us start this solution of the problem by considering, okay, let the MOSFET M1 be in linear region. So I'm writing the magnitude of current expression in linear region, which is mu P Cox by 2 WL into 2 magnitude of VGS minus VTH into VDS minus VDS square. So this is expression for the drain current in linear region. So we know what is the value of VGS. So VG is grounded, VS is at 1.8. Actually VGS happens to be minus 1.8. That's what is magnitude given as 1.8 minus this is VGS, which is magnitude wise 1.8. V threshold magnitude is 0.4. So VDS happens to be the drain to source voltage, which is nothing but we can actually find VDS is nothing but VDD minus ID into RS. So this is ID into RD. So whatever we have. So since we don't know that value of ID into this resistance 1K, so we are writing it as, so this is we are actually substituting the value of VDS in terms of VDD minus this drop. So this drop is actually the current flowing multiplied by the resistance 500 ohms. and again this VDS is substituted as 1.8. Now this exact expression of 1.8 minus ID into RS, which is 500 ohms, is nothing but the VDS expression. So upon solving this, we'll get two answers because we have a quadratic term. So we'll end up with minus 2.6 milliamperes as well as plus 2.76. Because minus is not a valid answer, we'll take 2.76 milliamperes as a valid answer. So since we are getting one valid answer, we can say that the MOSFET is operating in linear region. So let us just verify whether the MOSFET is operating in linear region, whatever that we assume. So let us substitute the value of ID, which is 2.76 milliamperes, which we got it from this, onto this, and then try to find out what is the magnitude of VDS. Magnitude of VD is nothing but 1.8 minus ID into the resistance 500 ohms. So this comes out to be 0.417 volts. So as we can see now, since this 0.417 volts is less than, so VDS sat is actually how much is VDS sat? So VDS sat is actually 1.4 volts. So it is this is actually VDS sat 1.8 minus 0.4, which is 1.4. So as we can see that since VDS is less than 0, sorry, it's less than 1.4 volt, it is like 0.417. The MOSFET is in linear region. I can see this is a B part of the same problem. So we have a different circuit diagram. Now you can see drain and the gate are shorted. So let us actually find out what is VGS. VG is nothing but VG minus VS. Whereas VG, the gate voltage, is nothing but ID into 1K resistance. That's what is written. That is VG minus VS is 1.8. So we can actually get the expression for VGS magnitude as 1.8 minus ID into RS. So this RS would have been RD because this is the drain terminal. So this is actually 1K. So we know that ID is given by mu PC of W by L into VGS minus VTH whole square. So let us just uh, give the expression of assuming the MOSFET is in saturation region. So we have substituted the value of VGS in saturation region, and then we are actually trying to solve for this. As we can solve here, we have two current equations, which is 2.31 milliamperes or it's 0.847 milliamperes. There are two possible answers because there's a quadratic term here. Suppose if you choose 0.47 milliamperes, so VGS happens to be 0.952 volts, so which is a valid voltage. Suppose if you take ID is equal to 2.31, the VGS happens to be, the magnitude of VGS happens to be negative, which is not a proper one. And as we can see that in this particular connection, as this VDS is equal to VGS, so MOSFET remains in saturation region, because whenever the gate is connected to drain, the MOSFET operates in saturation region. So let us see the C part of the problem 6.43C. Now here also we are asked to determine the region of a MOSFET. Now this is the region of MOSFET what we are supposed to find. So here also let us try to find out what is VGS. VGS, as we know that it is nothing but VG minus VS. So here VG is grounded. What is VS? VS is actually VDD minus RD into ID. So that's what is written here. So VG is 0. VS is VDD minus ID into RD. So we'll assume the expression for ID as magnitude of ID, because this is a PMOS transistor, we are taking the magnitude. So substituting that VGS as it is given over here. So if we solve for this, so it comes out to be 0.847 milliamperes. Of course, there will be one more value for that. So if you substitute that value over here, you get this VGS as minus 0.953, which is a valid voltage, because we are supposed to get a voltage VGS which is less than minus 0.4. So you're having it as minus uh, 0.953, which is far less than minus 0.4. So MOSFET is on now. So VGS is less than VTP of VTH of the P transistor. The MOSFET is on. So let us also try to find out what is VDS magnitude with respect to VDS sat. So VDS is 0.953 and VDS sat is 0.553. So since VDS is more than VDS sat, the MOSFET is operating in saturation region.